So as I was saying, we are going to we're going to be comfortable with the tension in each of the two strings being the same everywhere in each string. So T1 is T1 everywhere in the string, and T2 is T2 everywhere in the string. So then we have a look at like what it takes to move block 1. I'm kind of wondering, so I'm looking at the right hand side of the blackboard of this picture with the TA's head in the shot, and I'm looking at the TA's, so the TA's saying massless Pullian strings in extensible strings, T2 equals T2 prime, T1 equals T1 prime, and then the next line says 0 equals T2 prime plus T1, is that a prime? Ah, nuts, I can't tell what he's writing there. T2 prime, oh, those are just vector arrows on top of the T's. Okay, so 0 equals T2 plus T1 plus T1, and then he says 0 equals T2 minus T1 minus T1, and I'm not totally sure what the logic or the physics behind that is. Because if we're looking at a free body diagram of pulley 1, is that what he's referring to? No, okay, this does make sense. So pulley 1 has no mass, right? And okay, here it goes. And I'm thinking out loud, and I'm sorry I didn't prepare better for this one, but this is, like I said, a complicated problem. Okay, so pulley 1 has no mass, so we can't really apply Newton's second law to pulley 1, but we do have to conclude that we still have this issue. Like I'd almost sort of draw T2 like this, you know, sort of pulling up the plane, and then you have connection to the axle, and then you have T1 prime, who cares what you call it, and then S1 here, and T1. And it's almost like you're looking at this black box right here in your system, and you're saying, I don't really know what's happening here, but I sure know that I've got a pull on T2, and these are pointing back, both of these. Let's see, no, just kidding, this one's pulling up, right? No, on the pulley, it's pulling back. It's an action-reaction business, right? So if I'm looking at this block, and I'm looking at the pull of the string here, I have to say that T2 is pulling up the hill, and then out of my box I have to say that T1 and T1 prime are pulling down the hill at this magical mystery, you know, pretend box. T1, not T, wow, which is which? T1, yeah, right? This is T1 prime. So T1 is pulling the pulley down at the bottom of the pulley, and then as a reaction, T1 is pulling up the hill on S1. And that's why S1 receives an up the hill pull. But if we look at the box, we have to say that pointing out of the box, and up the hill, I have T2, and then I have out of the box And downhill, I have T1 and T1 prime. And I already argued that T1 and T1 prime are the same. So this is where he's coming up with this conclusion in the 1, 2, 3, 4, the fifth line on the right side of the blackboard. He says T2 is equal to T1 plus T1 prime, which is the same thing as saying T2 is equal to 2 times T1, right? Because T1 and T1 prime are the same thing. So this is like a long and complicated version of talking about a block and tackle system. And it's coming from the fact that the first pulley, pulley 1, has no mass. So we can't really apply Newton's second law here, but we can look at the forces. That's my son. Oliver is trying to be part of the video. So we can look at the forces sort of pointing in and out of this box and say, well, there's nothing that's actually being accelerated by these forces. So the out of the box and the out of the box forces have to be in balance. I think that's what our argument is going to be. And like I said, it's a complicated version of saying the same thing, which is that T2 has to pull against twice of T1 in order to move block 1. Okay, so that resolves then the kind of upper right side of the board. And then I'm looking at the lower left side of the board, and your TA is arguing that the velocity of block 2 has to be the same as the velocity of pulley 1, and the velocity of block 1 has to be equal to the velocity of pulley 1 divided by 2. And I'm not sure that we're given a very clear logic for that, but it kind of follows from our same argument of tensions that, so S2, let me make sure I'm trying to simultaneously read the screen with the picture from the TA and also look at my own notes. So we have block 1 connected to tension 2 with no stretch, yada, 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 and block 2 is connected directly to pulley 1. So that makes sense, right? There's nothing in between block 2 and pulley 1. Velocity of block 2 has to be equal to the velocity of pulley 1. And I think we can say from there that the acceleration of block 2 equals the acceleration of pulley 1, but we can maybe come back to that in a minute. And then we're looking at how the tension and or it's almost, and this may be, there's a picture of, the next picture in the series you sent me was a picture of the pulleys and the strings, and he's drawn something like L over 2 next to the what we're calling pulley 1. You can make an argument for the velocity of block 1 compared to the velocity of pulley 1, in that as pulley 1 goes up the hill, it goes up a distance L, but for every distance L that pulley 1 and tension 2, etc. go up, I have to pull half the distance of length tension 1. Let me make sure that does not sound very good right now, but L over 2 and L over 2. It's similar to the argument we just made about the tensions, where tension 2 has to be double tension 1. If I move 1 unit in the T2 sort of frame this way, right? This, because the string is wrapped around the movable pulley, only moves half that distance. There's a better geometrical argument I can make for this, but I can't come up with it on the fly, but it's something like that. So in any case, what we're going to conclude, if I can crowd out my diagram here, is that the velocity of block 2 is the same as the velocity of pulley 1, but the velocity of block 1 is only half the velocity, whoops, I'm misspelling pulley, of pulley 1. That idea that for every unit this string moves, this doubled up string only can move half as much. So for every velocity unit, that seems backwards, but no, for every velocity unit pulley or block 2 moves, block 1 moves double the velocity. I'm not totally convinced, and I may have to come back to this, but let's just follow this. So if we say, set these two equal to each other, right? So V pulley equals V pulley, pulley 1 equals pulley 1. So we're going to say that the velocity of block 2 is equal to twice the velocity of block 1. Let me think about that for a second. Block 1, yeah, that's totally it, right? Block 1 moves at half the velocity of block 2. Yeah, no, this is consistent. I don't know if this is run off the screen though, but so we talked, I didn't draw it, but in the last picture you have of the blackboard, your TA seems to be making the argument that for every unit of motion that like chord 1 moves up the hill, chord 2 can only move half as much because chord 2 is doubled over. So I have to conclude because of that, that the velocity of block 1 is half the velocity of block 2. Block 1 can only move half as much as block 2 for any given unit of time. Okay, I think I've made sense of that. I hope it makes sense to you. Okay, so if the velocity of 1 is, if the velocity of 1 is half the velocity of 2, and here's where I tried to write in pencil, if the velocity of block 1 in any time frame is half of the velocity of block 2, then we have to conclude that the acceleration of block 1 is half the acceleration of block 2. There we go. Okay, so we've got this kind of convoluted issue of adding the second pulley, making this funky block and tackle system. We have kind of a geometric argument. We get to this point right here, and we are now back to exactly the same free body diagram, Newton's second law shenanigans that we went to for the first set of solution. And my son and husband are getting antsy. So I think, and oh gosh, I'm about to run out of computer battery life. So I think I'm looking through the solution, and I think we're good to go. I think the only difference at this point from the original problem and this two-pulley problem is that instead of setting up Newton's second law for each block, same free body diagrams, we have no other things touching. We still have T2 touching only block 2. Okay, we do have the difference of T1 touching block 1, and T2 is equal to double T1, so we have to make that substitution. So we have two constraints now that are different. We have the acceleration of block 1 is half the acceleration of block 2, and then from before we have the tension in string 2 is equal to double the tension in string 1. We have the same free body diagrams, and we have these slightly different constraints, and you generate the solution from there. We do the same steps, and I'm going to stop here. Give me some feedback from this and tell me what other questions you have, and we'll see where we can go from here. I have my document camera for the weekend, so I can clarify this solution maybe, or try it again if you have more questions. Anyway, cheers to Friday, and I hope you're having a nice weekend. Bye.